Okay, so then we'll now talk about the pre-processing of the data after we received it from deep data store. So we go to the data. You receive this data here, data pre-processed MATLAB, which contains a whole bunch of MATLAB files, which then within each of them contains the data for each video or each trial, and then the labels from the questionnaires each participant filled out for valence, arousal, in these two columns here, 1 and 2. We then needed to put this into a format for our neural network to process. This involved a bunch of looping over the data and number of subjects, number of trials, 32 participants, 40 trials each, 40 videos. We select which channels of the EEG to use. These were obtained from various research reports that we looked up and found. Sampling frequency, which was specified on the DEEP website. We then set up the directories, so we tell it where to find the data and then where to put our processed data afterwards. We then start processing the data. So we load the data from the file that we showed up there. We then extract the channels we used to use that we set above. We then run a FFT on it. We do that on every trial for every subject. When we processed the data, there were 8,000 data points in the FFT, which we then downsampled to fit into the neural network. But we ended up, that's this one here, downsampling. We then ended up not using this downsampling. We then saved that into a new file. And then we also calculated the PSD of this data, because that was recommended in. It was what the DEEP original paper did in their classification and processing. Yeah, and then we also update a waiting bar to give feedback to the user. Yeah, we'll just run this. Yeah, and it runs on all the data. So this is our initial attempt at processing. We tried a lot of other things as well. So we go to this one. After we'd run the neural network a bunch of times and gotten subpar results, we got recommendations from Kari to split the data into chunks of 6 seconds. And also in the original DEEP paper, they only used the last 30 seconds of each trial, just for any sort of like startup time of the video, where it has no impact for the first however many seconds. And then in the last 30 seconds of the video, the emotion will have like kicked in. Yeah. We also tried different channels from different papers as well. So yeah, we also tried splitting up the. I'll come at this one. We tried splitting up each of the data into each of the alpha, beta, and gamma bands of mental capacity, in a sense, and then using that data in the neural network. But this proved to be too little data. It was too abstract. So we then split it into even more bands. Run that. Yep. So we also tried mean, and then the one we ended up with in the end was summing all the data. Gave us good results. So for the labeling of our data, we wanted to classify two characteristics: the valence, which is the positive and negative feeling of the emotion, and then arousal, which is the sort of intensity of the emotion. So the main classification was which quadrant did we sit in: 1, 2, 3, or 4. So it's fairly simple. The labels we were given in the data set were from 1 to 9. So we just say if it's above halfway, we label it one thing. If it's below halfway, we label it another thing. And then that for the 2 dimensions give us our final label.
All right. So for our classifier, we decided to use a convolutional neural network through using the deep learning toolbox in MATLAB. So the structure we used for the convolutional neural network was having a first layer which had a 1D convolutional filters, of size 32 by 1, and we had 256 of those. And the stride was 16 by 1, so we didn't have cross-contamination between the channels. So the first layer would only go down the FFT array for each channel. And we had this, and we had an areal layer and batch normalization to improve the results. And we used 2 more convolutional layers as well, which had size of 4 by 4, and we had 120 of the 8 of those with a stride of 1. And the last convolutional layer had 2 by 2 filters, 64 of those, and also a stride of 1. And they both had max pooling following them as well. And following all this was a fully connected layer with a softmax classifier. We used the same structure for both 4 classes and 2 classes, and we tested it with the PSD and FFT, and we found PSD was better for classifying between 2 classes, and FFT was better for classifying between 4 classes. We also tested using augmented input training data to reduce overfitting, because overfitting was a major issue due to the small data set. The training data will be quickly learned, and then the validation accuracy would just flatten off and not improve or get worse. But the augmentation didn't improve anything at all. It made everything worse. And we also tested some downsampling. We didn't find it really affected the results too positive, or it made it worse actually, using a lower resolution. We also attempted to use dropout layers to reduce overfitting, but that also harmed the results. One other thing we also tested was instead of a convolutional neural network, trying a fully connected network. All it contained was 3 or 4 layers of fully connected, 4 fully connected layers. 3 of them had 5,000 neurons each. There wasn't much change in the results. It was pretty similar to the convolutional neural network. And now I'll just run a training test just so you can see. This is using 4 classes, where we got an accuracy of I think it was 40%, around 40% for 4 classes. This will take a while, but you can see the comparison. The top graph shows training using 2 classes, so we got validation accuracy of 60%. We also stopped the training early because we found that improved results. Letting the training data get an accuracy of 100% would just reduce the validation accuracy. And in the case of 4 classes, you can see it's flattened out at 40%. And also training for the 4 classes is a lot longer. And that's it.
So finally, with our results, we took the confusion matrix and the ROC curve of our convolutional neural network, and we did that for both the 4 classes and 2 classes. First, we'll start with the 4 class, and we see here in the confusion matrix that our neural network was better at telling us which was the true negative rather than telling us the true positive. As you can see in the curve, as that red percentage is more clear in each class. For example, in class 2, you can see that it has the better percentages in telling us the true negative, as it has an 88.6%. And this correlates perfectly with the ROC curve, as class 2 is the closest one to the top left corner of the ROC curve. This also relates to class 4, as this class has the smallest percentage in terms of true negative percentage. And this can be seen in the ROC curve, as this value is the closest to the midline of the ROC curve. Then also in terms of probability, we can check that class 4 is better at telling us the true positive, or selecting which emotion is felt by the patient rather than telling us which emotion is not felt by the patient.
Also in the top is a test of input data that the neural network hasn't seen, and it has correctly classified the data as class 4.
Okay, so for our second option, we did also a two-class classification matrix, convolutional neural network, sorry. And in here, we also did the confusion matrix and the ROC curve, plus the class probabilities. In the class probabilities, we mainly focused on what would happen if a singular input never seen by the confusion matrix is seen. What would be the probability of the neural network selecting which class would be more probably like to? So in this case, we can see that class 1 has a 60% probability of being labeled, or class 3 has a 40% chance of being labeled. Similarly, with the confusion matrix, it's the complete opposite of the four-class neural classification neural network, because in this one we see how it was better at actually predicting the correct values rather than discarding the incorrect values. So this can be related to the ROC curve, as the ROC curve has a very positive area. So to finish this 2x2 confusion matrix, we found that our sensitivity of our model it's approximately average, taking into account that for class 3 it has a 64% accuracy in telling us the true positive, and instead for class 1 it has a 47.8% of telling us the true positive. However, in terms of the ROC curve, we can see that overall the model is very good at predicting for class 1 and class 2, which is a true positive percentage according to the new input values. This also relates back to the class probabilities, as when a new input is sent to the model, it's telling us that class 1 has a higher percent of being selected rather than class 3.
1 week later.
All right. So finally, to conclude, we tried two different models, all using the convolutional neural network. We tried 4 classes and then 2 classes, and we figured out that we have a higher specificity and sensitivity when we're using 2 classes, which should be obvious, as we're having less data and like the classification is easier. However, when we took into account the dimension of arousal instead of only taking into account valence, we found that by splitting the data into frequency bands, into the small chunks, as Tim mentioned, that gave us better accuracy in terms of the curves, as more data was extracted from each FFT. Also, including the PSD, it has a very strange relation when we did the first model, as when we did FFT in the 4 class, the FFT had better accuracy, but when we tried the PSD, it was worse in the 2 class classifier. Finally, to make some final remarks, we would suggest to try this model with more data, as only 40 videos crippled a lot the progress of the convolutional neural network. So what we did to solve that was split data into smaller chunks and pre-process that data as its own to figure out which was the better classifier. Now, some future work would be using a different algorithm than convolutional neural networks, like closest neural network, or MLP-NN, as these neural networks are highly used across the literature and has the highest % accuracy. Thank you.
Yay.
Right. I have a thing here. It says specificity measures how exact the assignment to the positive class is. In this case, a spam level assignment is okay. So that's that example. And then the sensitivity, it means it's about 88%. And then okay. It's so complex, and why they have to name it the same thing? Like they could have just tell you this is correct and this is incorrect. Like, why they put the same names and like they sound exactly the same when you say that?
Yeah, exactly.